Hi, most excellent rock buds. It's Rock Papa. Hope you guys are doing well, and happy holidays to every one of you guys. You know, we've been talking about the many faces of quartz and the many faces of calcite. Now we're going to talk about the many faces of iron in all its forms. The reason I'm talking about these three elements slash minerals is because they're so abundant and so common in the earth and have so many different forms. They also interact with each other. For example, iron impurities provide the colors for a lot of the beautiful quartz examples and chalcedony examples, that sort of thing. So we're going to talk about the many forms of iron and including some that you're very familiar with, for example, such as our own blood that runs through all of us. So I hope you guys like this video and it's useful. So please subscribe. Thank you a million to all my wonderful subscribers. Think about you all the time. Here we go, the many faces of iron. Iron is an element and iron is a metal. Iron is super abundant in the earth. The earth's core is made of iron and nickel, and all that iron in the core of the earth is what makes the earth a gigantic magnet. Elemental iron readily forms bonds with oxygen and hydrogen to form iron oxides and iron oxyhydroxides, and we'll talk about some of those soon. So, most excellent rock buds, my question is, where does all this iron come from? Let's have a look and see. Rock friends, as you know, this is granite, and granite is a very felsic rock. That means it's high in quartz, but it's also got a lot of black dots in there. Let's figure out what they are. Granite gneiss, which as you know is the metamorphic version of granite, also has black crystals in it. I know you know this mineral already. It's biotite. Let's see what biotite is made of. As you can see, biotite has some iron in it. Not a lot. We will say biotite has a little bit of iron. Hey guys, yes, biotite has a little bit of iron in it, but because granite and granite gneiss make up the majority of earth crust, granite and granite gneiss release a lot of iron into the environment via weathering and erosion. Here we have a hand sample of diorite. Diorite is an intermediate pluton. And along with andesite, its above ground equivalent, it is chock full of hornblende. And hornblende has a pile of iron in it, more iron in it than biotite. Diorite and andesite are very abundant in subduction zones and island arcs, as well as continental volcanic arcs. Think of the Andes Mountains. Andes are made of andesite. And think of the Sierra Nevada mountain range in California. It's made of a bunch of diorite. Gabbro pluton and its above ground equivalent basalt lava are mafic rocks. That means they're very high in iron and magnesium. And pyroxene is the mineral that contributes most of the iron in gabbro and basalt. And just as a review, you've got a piece of ocean crust on the right subducting under the edge of a continent. It's creating a volcanic island chain, and fractional melting is occurring there, producing felsic, intermediate, and mafic volcanic rocks, all of which contain iron. Over millions of years, this iron-rich material erupted from volcanoes, is acted upon by the forces of weathering and erosion, and washed into the sea, where it combines with oxygen and hydrogen to form the four main iron compounds we find in nature. So let's have a look at those four main iron compounds we find in nature. I'm talking about the four ites: goethite, limonite, hematite, and magnetite. Goethite, also called bog iron, provided the iron ore that kicked off the Iron Age, which began around 1000 BC plus or minus. Here's some pictures of bog iron, and as the name implies, bog iron forms in bogs and swamps. Back then in Iron Age Europe, the rich folks would send guys out to search for bog iron. Not the funnest job in the world. They would wade through these bogs with a long, sharp stick, and they would look for signs of iron, like orangey water, and also kind of a rainbow color that indicated the presence of iron dissolved in the water. Then they would probe into the bog with their long sticks until they hit something hard, hoping it would be a lump of bog iron. It would take about 20 bog iron lumps to form enough ore for forging something like a useful tool or perhaps a sword or spear point. Researchers believe that bacteria are involved in the process of forming this bog iron. Here are some Iron Age swords. Now let's take a look at limonite. Limonite often forms when you add hydroxide and water chemically to hematite and magnetite. It comes in orange colors and yellow colors that in prehistoric time were used for pigments. Limonite can also form from the breakdown of iron pyrite, also called fool's gold. And like gold, silver, lead, copper, and other valuable metals, pyrite is produced by volcanic activity associated with hydrothermal fluids like hot water. In the old days, gold miners used to look for limonite on the surface of the ground, which indicated the very possible presence of valuable metals buried below. They called this orangey yellow limonite staining Gossan, G-O-S-S-A-N. And here's how that Gossan gets there. This funky drawing is a little hard to see, but I'll try to explain it. The red oval represents a large body of magma that has intruded into layers of limestone. The black squiggly lines radiating from the magma body are cracks that are filled with magma and hot fluids enriched with all kinds of valuable metals, including lots of iron pyrite. Over time, perhaps millions of years, the upper layers of soil are eroded to expose the surface of the black enriched cracks, and the iron pyrite is weathered into yellow and orangey limonite staining called Gossan. In the meantime, percolating water has picked up the valuable metals like gold and silver and taken them down to the water table directly below the Gossan exposure. Here's some examples of Gossan stained rocks indicating valuable metals below. Hematite is iron oxide, and it comes in colors ranging from black to red to orange. This is banded iron formation, and it is made of hematite, and it is the main source of iron ore worldwide. 30 or 40,000 years ago, our ancestors were using it as red ochre in Paleolithic cave paintings and in ancient burial ceremonies. And if, like me, you live in a place where the soil is red, that red color comes from hematite, which is developed from the erosion and weathering, most likely of granite and granite gneiss. Here are some examples of hematite-rich quartzite laid down during Ordovician time, when the taconic orogeny mountains were eroding tremendous quantities of sand and iron into the shallow ocean of the Foreland Basin. Back then, there were no plants on Earth to stem the tide of all these sediments. Now, rock buds, we're in Moab, Utah, looking at the Wingate Sandstone Formation, deposited back during the very beginning of Jurassic, when hematite-rich sand piled up in massive sand dunes that were later pressed into red sandstone. And I really do know how to spell sandstone. Ha! What about magnetite now? Magnetite is an oxide of iron that has magnetic properties, and that's why the ancients called it lodestone, which means stone that shows the way. Magnetite is usually blackish, and here are some examples. Hey rock buds, I want to know what makes magnetite magnetic. Let's look into this. In most elements, the electrons that compose them spin in opposite directions from each other. This cancels out any kind of magnetic charge. In contrast, the electrons in magnetite all spin in the same direction, imparting a magnetic charge. Picture some molten magma that has a lot of magnetite in it. The electrons are spinning like crazy, all in the same direction, and the magnetite has a magnetic charge. All these tiny molten magnetite magnets line up with the magnetic field of the Earth, and when the rock cools, they're frozen in that state. And so you get a magnet that metal things will stick to, and that magnet will also align itself to the magnetic poles of the Earth. Here's a compass made by ancient Chinese navigators. And here's one that uses a big hunk of magnetite on a floating board. This animation shows how ocean crust produced at a mid-ocean ridge records the change in the Earth's polarity over time. As each batch of ocean crust cools, the magnetite in that ocean crust permanently aligns itself to the polarity of the Earth, thus making a record of the changes in the Earth's polarity. And since we know that ocean crust in the mid-Atlantic ridge expands at about 1 inch per year, we can tell that the Earth changes its polarity about once every 300,000 years. Hey, most excellent rock buds, a few more interesting facts about iron and we're done. And as you guys know, we can't live without iron because the iron in our blood is what takes oxygen from our lungs and distributes it to every cell of our body. Pretty slick, eh? The color of the iron staining in rocks can tell us a lot about its depositional history. The sand in this sandstone was deposited in a hot, dry climate where the iron in the sand was oxidized to this beautiful red color. On the other hand, this sandstone was deposited during a cold, wet period of time, and so the iron in the sand has not been oxidized to that red color. And finally, as we've seen in other videos, the presence of minute quantities of iron impurities combined with trace amounts of other elements gives beautiful colors to our gemstones. Okay, most excellent rock buds, that's it for iron. Thank you so much for watching. If this video was helpful to you, please subscribe. And this here is your Rock Papa, wishing you happy holidays and happy rock hunting. Papa out.